This is a lesson on kinematics, conversion of a kinematics graph. For this lesson, we'll be interpreting and converting kinematics graph. So the specific example is displacement time to velocity, velocity back to displacement, velocity to acceleration, and acceleration to velocity time. So and of course we'll be doing for mainly these three types of motion: stationary, when object is traveling at uniform velocity, and when object is traveling at uniform acceleration. In order to convert the kinematics graphs, we just only need to remember and apply these two important concepts: that velocity is the gradient of the displacement time graph, acceleration is the gradient of the velocity time graph. Okay, so let's move on to stationary object. It's relatively simple, but let's just object stationary means the displacement is a constant value. It can be 0, positive or negative, but it all has a pattern that is a flat displacement time graph at the starting displacement. So it's just a flat line. So it could be positive, it could be 0, or it could be negative. So all this type of graph would have the same velocity and acceleration as illustrated. So since it's not moving, velocity is 0 at all times. Velocity time graph would be a flat line, and since there's no change in velocity, acceleration would also be 0, which means that acceleration graph will be a line. Another way to derive these graphs is to base on the based on the displacement time graph, and we derive from there. So the displacement time graph is a flat line, so the gradient of the graph is 0. Since the gradient is 0, but we also mentioned that gradient is the velocity, means that the velocity time graph would also be a 0. Similarly, if we establish a velocity time graph is a flat line, which means that the gradient is 0, since acceleration is the gradient of the velocity time graph, then the acceleration time graph will also be a flat line. Let's move on to uniform velocity. Object moving at uniform velocity means that the velocity is a constant value, so it can be positive or negative. Just go directly into the velocity time graph first, because that's the simplest to sketch. So it would be positive or it could be negative. In this case, it couldn't be 0 because as in 0 velocity at flat line we already covered. Okay, since it is actually just a stationary object. So since it's at constant velocity where there's no change in its velocity, acceleration equals to 0. So the corresponding acceleration time graph would be just a flat line. Alternatively, of course, we can also utilize the idea that acceleration is the gradient of velocity time graph, and since the gradient of the velocity time graph is 0, which means the acceleration equals 0, and thus result in the acceleration time graph being a flat line. Okay, so again, if we apply the idea that velocity is the gradient of displacement time graph, we can convert uniform velocity time graph into its displacement time graph. Since velocity is uniform, it means that the gradient of the displacement time graph is constant. It means that the shape of the displacement time graph would be a straight line, because only a straight line would fulfill the idea that the gradient of the graph is a constant or uniform. So it would be something like this, or it could be something like this. So I'm sure you can right now infer that for this is a positive gradient, so which means that the velocity is positive. In this case, this is a negative gradient, the velocity is actually negative. But that's actually not the final displacement time graph, because it really depends on the question itself of the starting displacement. The previous graph actually assumed that the starting displacement is 0, but it could be others. It could be positive or negative. So if you find that if you have a positive velocity but you have a different displacement but it's positive or negative, what you simply need to do is just to shift the entire line up. Okay, this means that it starts off with a positive displacement, and it could also start off with a negative displacement. But you realize that this is always positive gradient, and which means that it is positive velocity. Likewise, it is the same for a negative velocity. So the negative velocity can have positive displacement or negative displacement. So this means that it is a positive displacement, and this is a negative displacement. Okay, so then converting displacement to velocity time graph. Since we can convert a flat velocity displacement velocity graph back to a straight line, so it means that the other way also means correct. Okay, it means that if you have a straight line, a displacement time graph, the corresponding velocity time graph must be a flat line. Okay, it works both ways. So any displacement time graph that have a positive gradient will have a velocity time graph that is of a positive value. Likewise, the opposite is also true. And that's the idea that that stems from the idea that velocity is the gradient of a displacement time graph. Let's move on to uniform acceleration. Object at uniform acceleration means that acceleration is a constant value. It can be 0, it can be positive, or it can be negative. But 0, of course, is the previous case covered. So we'll be focusing on positive or negative would be value. Since it's constant, it means that it will be a flat acceleration time graph. So we focus on the acceleration time graph, then we convert to velocity time graph, then from velocity time graph convert to displacement time graph. So this is simple, just a flat line. So it can be positive, it can be negative acceleration. Again, by applying the acceleration time graph, acceleration is the gradient of velocity time graph. We similarly to the previous case, we can convert uniform acceleration time graph into its velocity time graph. Since acceleration is uniform, which means that the gradient of the velocity time graph is uniform. So in this case, the shape of a velocity time graph is a straight line. And there are two. So again, it is similar. Okay, but take note that this time now, this is velocity time graph. Okay, velocity time graph is right now a straight line. We focus on the uniform acceleration, how to convert velocity time graph, which is a straight line, to its displacement time graph. Again, it is the same idea. So this time round, the shape of the corresponding displacement time graph would generally be a curve. For those that are interested, the shape actually is a quadratic curve. Why is it a curve? It's because since velocity time graph is a straight line, it implies that the velocity is always changing its value, which means that the gradient of the displacement time graph is always changing, and only a curve fits that description. A curve has its gradient is always changing from one value to the other. The actual of the shape of the displacement time graph would depend on, of course, the acceleration, whether is it positive or negative. We also pay attention to the starting velocity value, whether is it 0, positive or negative. And for this lesson, we'll only go through structure in such a way that it is positive acceleration, and you have a starting velocity to be 0 and starting velocity to be negative. What about starting velocity to be positive is assumed under this is because it has a similar shape. Then we move on to negative acceleration. Same thing, we have a starting condition of starting velocity is 0 and starting velocity is positive. Then okay, this is a negative has a similar shape. Okay. This time around, we just assume that all starting displacement to be 0 to lessen the complication. Okay, let's start with positive uniform acceleration and starting velocity to be 0. Since this would be, as described, this will be the velocity time graph for a uniform positive acceleration, and the velocity value will be increasing at a constant rate. So the displacement time graph will simply just be a curve in this manner. And since let's start. Okay, since the starting velocity is 0, so we find that the starting gradient is a flat line. But the gradient of the displacement time graph is increasing, as you can see from the graph. Okay, you find that it becomes steeper and steeper. Okay, so the shape of the displacement time graph would take this form. Okay, where it is 0, is becoming steeper and steeper. As I mentioned before, if you have a starting positive velocity, you find that actually what it means is that you have a shape like this. Okay, a straight line parallel. The shape of the graph is roughly similar, except that it doesn't start flat. Okay, you will have a curve that is much more steeper, and since it's also steeper all the way, the graph will be a graph like this. okay, it will be much steeper, but the general shape is pretty similar. Okay, what about if the starting velocity is negative instead of 0 or positive? We find that because of the acceleration or positive acceleration, the velocity value will be increasing at a constant rate. But since you start off with a negative velocity, the magnitude will be getting smaller and smaller. So if you start off from -5, it become -4, 3, 2, 1, and eventually it will reach 0. So it means that the object is actually traveling slower and slower. So if we start off the displacement to be 0, this will be the shape of the graph corresponding. Okay, how do we interpret that? With a starting velocity, negative velocity, the starting gradient of course will be negative. So it actually already has some negative gradient. Okay, but you find that since the value becomes smaller and smaller, it means that the gradient becomes more and more gentle, and eventually the displacement, the gradient will be flat, okay, which is 0 velocity. Let's move on to negative uniform acceleration. The starting velocity is 0. So in this case, the velocity value is so-called decreasing at a constant rate. It becomes more and more negative. So if you start from 0, it becomes -1, -2. Okay. So in this case, actually, the object is actually increasing. It's becoming faster and faster because the magnitude is increasing. So for displacement time graph, you find that it's actually the flip of the previous case. Since your starting velocity is 0 meters per second, then the gradient is actually 0, but it will become more and more negative. Okay, so it means that the graph becomes steeper and steeper, but in a more negative sense, negative gradient. Okay, it become more and more steeper. So that's why the curve is this picture. So for starting velocity, which is positive, so you have a positive starting velocity, but you have a negative gradient, which is negative acceleration. The velocity value is right now decreasing. It's still decreasing at a constant rate, but since it's positive, so you have a maybe +5, then you become +4, +3, and so on and so forth until it reaches 0. So the magnitude in this case is getting smaller and smaller. So the object is actually traveling slower. The corresponding displacement time graph would be this pattern. Again, it is a flip of one of the case. With a starting positive velocity, so you have a positive gradient. So this is a positive gradient. But you find that the positive value becomes smaller and smaller, so the slope becomes more and more gentle until it reaches a high point, which corresponds to here. So these are a summary. I'll just flash them for 2 seconds. If you need to review, you just look at it. So the blue line represents this. Okay, this is some practice questions for you. So if this is a velocity time graph, okay, and you have all this value, are you able to convert and sketch the following this velocity time graph into its corresponding displacement acceleration time graph? I would suggest you trying to sketch the acceleration time graph first, okay, because it's easier. Then you try to sketch its corresponding displacement time graph. Okay, that's all for this lesson.